In the last video, we learned about Kirchhoff's rules, which is used to help solve for the currents and the voltage drops across resistors in a complex circuit. In this video, we're going to actually look at those rules and apply them. Again, the two rules for Kirchhoff's rules. The first is the junction rule, which states that the currents going into a junction have to equal the total currents coming out of a junction. And the second rule is the loop rule, which states that any loop within a circuit has to have a total voltage of 0. So we'll go through and apply those two rules to solve for the current and voltage drop across this circuit. All right, first of all, we pick the junction rule. First thing we need to do is determine the direction of currents through each resistor. Now, this is arbitrary. I would say just pick a direction. If you're incorrect with the direction, the current will come out negative, and that negative tells you you've got the wrong direction. So let's just assume that the directions of the currents go as you see here in this picture. All right. The junction rule says that when you pick a junction, we'll say junction A here, that any currents going in have to equal the currents going out. Okay, so pick that junction. What currents are coming into that point? The only current coming in is I3. All right, and that has to equal the total currents coming out. From that junction, you have both I1 and I2 coming out of that junction. All right, now what if, for some reason, you had decided to pick this point instead? Well, that works still too, because then you have I1 coming in, I2 coming in, and I3 going out like so. In which case, I in equals I out. In this case, you have I1 and I2 coming in, and I3 going out. Notice that's the exact same equation. So really, it doesn't matter which junction you choose, you should get the same result either way. All right, so that's our first equation. Now we use the loop rule to get our second and third equations. So in the loop rule, pick any loop. We're going to start simple and say we've got this battery here, E2, which has an internal resistance of 1 ohm. And we're going to follow a loop all the way around like so. Follow this loop. Now, just for simplicity, since this is I3 going through here, we're going to call this R3. I2 is going through this one, so that's R2. I1 is going through this, so that is, R1. All right, so remember that in a loop, you have voltage added by an EMF, and then you subtract any voltage drops across each resistor. So in this case, in this loop, you have an EMF, E2, of 45 volts. That supplies the voltage. And then you lose some voltage across the internal resistance. Then you lose voltage, excuse me, you lose a little voltage across R3. Then you lose more voltage across R1. And then that loop comes back to the battery. That total voltage, or that equation, has to equal 0. Now, we're going to simplify this equation a little bit by using Ohm's law, which says that V equals IR. So the voltage drop across your internal resistance would be I3 times little r. And your voltage drop across resistor 3 would be I3R3, and voltage drop across resistor 1 would be I1R1. I'm going to simplify this a little bit more by combining little r and R3. All right, and so now we have an equation here for one loop. Now, we have two equations. We have this one from the junction rule, that I3 equals I1 plus I2. We also have this one from loop rule. But remember, since there are three unknowns, I1, I2, and I3, then we have three unknowns. We need one more equation in order to solve for everything. So we're going to do this again and find a second loop. It is easiest to draw a loop that follows the same direction as the currents. So this time we're going to start with E1 and go around a loop in this direction. Okay, so we start off with EMF1, so E1, and then you have a voltage drop across the internal resistance of 1 ohm, and then you have a voltage drop across R2. Remember that we called this one R2. This was R3, and this was R1. So you have R2, and then after you hit R2, you hit another battery. That supplies a little extra voltage. And then you have another voltage drop across the internal resistance. Excuse me, that's not V times R, that's V sub R. And then another voltage drop across R3, and then you get back to EMF1. That total equation has to equal 0. Once again, Ohm's law says that V equals IR. This would be I2 times R minus I2 R2 plus EMF 2 minus, in this case, I3 times little r minus I3 R3. So just as a point, this I2R goes with this little resistance where you've got I2 passing through it. And this little r corresponds with this resistor up here, which has a current of I3 running through it. Okay, just like we did last time, we can simplify this a little more. Pull up my red again. We can pull out, factor out the r's. Factor out the currents. And this simplifies it like so. Excellent. So here are the three equations that we got from this, from using the junction and loop rules. First is that I3 equals I1 plus I2. The second one is that EMF2 minus the voltage drops across internal resistance plus R3 minus the voltage drop across R1 has to equal 0. And also that EMF1 minus the voltage drops across internal resistance and R2 plus EMF2 minus the voltage drops across internal resistance and R3, all of that has to also equal 0. Okay, so we are now going to make sure, or we're going to use these equations to solve for a variable. Now, the easiest method to do this is to look for the one variable that's in all three equations. The one variable that's in all three equations is I3. So we're going to solve everything in terms of I3, which means that for these equations here, we need to solve for I1 and I2. And so when you do that, you end up with these formulas here that I've shown here on the screen. It's a simple matter of adding the I1 term to the other side, dividing by R1, or adding the I2 term to the other side, dividing by R plus R2. Now, once you have these, we can take I1 and I2 and substitute them into the junction rule equation, and you get this equation. Looks nasty, but won't be too bad. So now it's a matter of solving for I3. Okay, so here's how that works. We're going to simplify this equation to look like this. We're going to separate all the terms so that we only have individual terms, not multiple terms divided by a large, all combined over a single denominator. It's E1 over R2 plus R plus E2 over R2 plus R minus I3 R plus R3 over R2 plus R. The reason we want to do that is now we can take these I3 terms and add them over to the other side. So I3 plus I3 R plus R3 over R1 plus I3 R plus R3 over R plus R2. I flipped them around from R2 plus R. It doesn't matter. Addition is commutative, so we're good. And that equals whatever's left, which would be E2 over R1 plus E1 over R2 plus R plus E2, over R2 plus R. All right, so now we can factor out I3, which would be 1 plus R3 over R1 plus R3 over R plus R2 is equal to E2 over R1 plus E1 over R2 plus R plus E2 over R2 plus R. Now, at this point, it gets rather complicated. You can see there are a lot of variables to keep track of. I'm perfectly fine if at this point you decide we are going to plug in our numbers. So remember that we said here that R2 was 20 ohms, R3 was 40 ohms, and R1 was 30. So R1 is 30, R2 is 20, R3 is 40. Let's just write these up here. R1 was 30, I already forgot, there we go, 30, 20, 40. And then all of your internal resistances are just 1 ohm. In which case that would be I3 of 1 plus R3 plus R. R3 is 40, so that would be 41 ohms divided by R1, which is 30 ohms, plus R3 plus R would be 41 ohms, divided by R plus R2 would be 21 ohms. And that equals E2. Should write that down as well. E2 was 45 volts, E1 was 80. Excellent. So E2 was 45 volts over R1, which is 30 ohms, plus E1 is 80 volts over R2 plus R. R2 is 20 plus the large 1, so 21 ohms, plus E2, which is 45 volts over R2 plus R. We just saw that was 21 ohms. Now if I simplify this, here's what you get. You get that 4.319 times I3 is equal to 7.4524 amps, which means if you divide by 4.319 on both sides, you get that I3 is equal to 7.4524 divided by 4.319 gives you 1.725 amps.